Thank you, Jen. I'm also really excited, not only because Dinosaur was awesome last year and the lineup this year really rocks, but also because Jen is doing the introductions. And like 3 years ago, when I was a fairly junior developer, Jen was my role model. I'm like, I want to meet Jen. So being here, meeting her in person, and getting an introduction is like even more humbling than just a great conference would be. So in the spirit of what Jeremy said, we should always be learning. So you have the opportunity now to learn about something that you probably don't touch much to in your day-to-day life. But we'll look at JavaScript engines and how they work under the hood. So as Jen said, I work on Chrome in Germany. The V8 team is mostly in Munich. So most of what I'll tell you is fairly specific to Chrome, but the overall principles, they apply to all the JavaScript engines. So I don't need to tell you that JavaScript is everywhere. I mean, it's the language of the web, but it's not restricted to the web. It's in Node.js. It's on IoT. Cass is doing a workshop on IoT tomorrow. There's an NPM talk, so Node is also, JavaScript is also a lot of tooling. It's everywhere. It's awesome for beginners. It's good for prototyping something quickly. But we also have enterprise node servers. We have massive production React frameworks. Like, we do so much with JavaScript. And so one thing I want to point out is this statistic here. 100x improvement in JavaScript performance since 2001. This statistic is already a few years old. Just want to say we get this much faster. And this is really important because imagine you had, well, think about the JavaScript that you write, and then imagine it were 100 times slower. Like, it would probably be useless. And without this speed up over the last decade, JavaScript, I think, would not be where it is today. So this performance is important. And all the performance of JavaScript comes down to the JavaScript engine that runs your JavaScript. So I think it's important to, or what I want to tell you is what the tricks under the hood are in the engines that the compilers do to give you speed up like this. Why are we 100 times faster than 10 or 15 years ago? Just to put V8 a little bit in perspective, there's many JavaScript engines. All the big browsers have their own engines. So there's Chakra Core and Microsoft Edge. There's V8 in Chrome. In Apple Safari, it's JavaScript Core. And in Firefox, it's SpiderMonkey. And it's good that we have competition, because without the competitions, the JavaScript engines would probably not adhere to the JavaScript standard. They would just be like, oh, that's a little easier, and then that would make everybody's life harder in the end. And the competition helps with performance. As long as there's competition, all the engines try to be faster, which in the end enables you to write even better JavaScript apps. And then obviously, JavaScript is not only in the browser. If you use Node.js, that's also the V8 engine, but there's also a Chakra node, and there's a Spider node fork. If anybody doing Electron is Chromium, so that's V8 engine under the hood. And then IoT. A lot of times, or sometimes you need to make a trade-off between performance and memory size. So on small devices, you might not use one of those big engines, but use duct tape or Samsung's Jerry's script. So lots of engines. What I talk about sort of applies to all of them, but most of it is very specific to V8, since that's what I work on. So how do compilers work in general? So any compiler, you always start with source code. You're compiling some kind of source code. And you need to parse the source code. Most compilers, or most parsers, generate an abstract syntax tree. That's a representation of your source code that is then easier to work with for the compiler. And then a compiler, or sometimes it's called an interpreter, takes this abstract syntax tree and converts it into executable machine code. Because somehow you need to go from something that is written on a, I'm going to say piece of paper, but obviously in an editor, in a file, and that needs to be turned into something that can be executed. So that is what, for JavaScript, a JavaScript engine is doing. There is lots of tools that compile something to JavaScript. Like if you think of TypeScript, there's a compiler that compiles that into JavaScript. Or if you think of ESNext features that are not yet in the browser, there's Babel plugins for that, CoffeeScript, all these things. So there's compilers that compile from something to JavaScript, and then there's the JavaScript engines that actually run that JavaScript code. And so the first part of this compiler tool chain, the parser talk, I'm not going to cover this. My coworker Maya did a really great talk on that, so if you want to learn some of the neat little tricks and in and out quirks of JavaScript parsing, I can recommend this talk. But we will focus on the second part here on the compiler and interpreter with a focus on performance. So what all modern engines use is a so-called just-in-time compiler. It's often abbreviated as JIT. You can turn it into a verb and JIT your code or have JITted code. And that means you're compiling just in time as you need the code, as you run it. And you're switching all the time between compiling and runtime. So you parse and compile a little bit of code, and then you run it, and then you keep on compiling. You're not compiling everything ahead of time and then run all that. You keep switching between compiling and running. Oh, sorry. Sorry. Should I put this lower, or is it okay? Okay. I'm gonna try not to breathe, so. Okay. All right, so just-in-time compilers are the thing for JavaScript engines that gives them a lot of speed, because we compile and run a little bit, and then we get information during runtime. Like we get the information, which functions are we running, or what are the inputs, and then we use this information to compile further on. That's one of the big tricks that gives us speed. So if we look at this picture again, for JavaScript engines with just-in-time compilers, we get this loop here going back and forth. So we're not doing parse AST machine code. We say parse AST machine code, compile some more different machine code, and we keep doing this over and over. So we're not compiling ahead of time. It's important that this is happening at the same time, or it keeps switching all the time. So that is one thing that gives JavaScript engines this 100x performance compared to 10 years ago. But that is not quite enough. So the other thing that all the modern engines have is an optimizing compiler. They have a baseline compiler, one for the slower warm-up and the not so important functions. And then they all have at least one optimizing compiler. Safari has even 2 optimizing compilers. And what they do is, if you have functions that are being run a lot, we call those hot functions, then those get passed on to the optimizing compiler, and then the optimizing compiler is recompiling those into better machine code. So it's a little more expensive performance-wise to recompile them, but you get something that is much faster. So I think it's obvious to see why you can't put everything in the optimizing compiler in the beginning, because that would really take a long time to compile it. You only do that for the hot functions. So that's another point why we need to switch between compile and runtime, because otherwise you wouldn't know which function is actually hot, what is even run a lot. So this picture gets more complicated. So of course we start with source code, we parse it, we get an AST. But now we have 2 compilers. And first we start with the baseline compiler, the sort of slower one, or the one that generates slower machine code. And if functions are hot, then we go over, if functions are hot, then from the baseline compiler we go over to an optimizing compiler. And in some engines we go even farther to the right into the next optimizing compiler. And so in V8, some name dropping, our baseline compiler is called Ignition. The optimizing compiler is called Turbofan. That is our new compiler pipeline. We just turned it on this year. So if you've heard older talks or read blog posts, a lot of that is not true anymore because we have this new pipeline. And if you ever hear anybody talking about turbofan and ignition and it's not about vehicles, then they're probably talking about JavaScript engines. Okay, so far the theory. We have code, we compile it a little bit, we run it, we use this information, run it some more, go on to the optimizing compiler. Let me try to clarify that with an actual example. So very simple function here, add, takes an object and it returns 1 plus object.x. Okay, simple enough. And we're actually just focusing on the plus here. So the plus symbol, intuitively, every kid knows that is for adding numbers. It looks very simple. It's a tiny little operator. But if you look at the specification, so don't worry about reading all the steps in the specification. This is the ECMAScript specification, which defines what JavaScript should be doing. And this is the addition operator defined in there. And you can see it's 10 steps. It looks really long. And actually, all the steps in between call other definitions, or they call other functions that, again, have a long definition. So something as simple as, something as simple as a plus is really long in the specification. And obviously, as a JavaScript engine, the compiler has to do exactly what the specification says. Otherwise, it wouldn't be JavaScript. So the compiler has to do all that. My coworker wrote up the whole thing. Like, this is the maze that the compiler has to follow for doing something plus something else. So you can imagine, performance-wise, this is not very easy. And I think this is kind of cute. There's a note at the top here. The addition operator either performs string concatenation or numeric addition. So we all know that it's addition, and sometimes you concatenate strings. But the specification is so convoluted that the editors decided they need to put in a note so that you can figure out what plus is doing. So that's how hard plus is for the poor JavaScript engine. So if you have a tiny little a plus b somewhere in your code, it's not as easy as you might think it is. It's this whole big maze for the compiler. It's like tons of steps it has to follow and checks, and there could be errors, and it needs to do two-string conversions and all of that. But think about it intuitively. If you're adding two whole numbers, that is basically what computers have been built for. I mean, it's not binary format, but some integer plus another integer, that is really simple for computers. Even if it's floating points, I mean, you have a few funny rounding errors in JavaScript, but adding up decimal numbers, that is still easy for a computer. String concatenation, again, it's nothing crazy. It's nothing that should require this maze of 20 functions. So it would be really nice if a JavaScript engine, instead of doing this whole maze, could do the simple stuff. Because if you do 5 plus 7, it should be simple. It shouldn't be follow 2,000 steps. And so this is the trick that we're actually using by using information from running and compiling and going back and forth. So let me show you how that works. So we're calling this add function a few times. So if you remember the add function, it will just return 7 plus 1 for the first line. Really not too hard. But when the compiler sees this for the first time, it has to follow the specification, do all these steps to figure out, OK, I should return 8. So we're calling this function a bunch more times. And eventually, the compiler is like, oh, looks like I'm always getting integers. Why am I doing all this extra work of figuring out if it's a string and like all crazy things and error checking? Let me just do regular integer addition, which is really cheap on machines. So we pass on this code to the optimizing compiler. We tell the optimizing compiler, hey, optimize this. And assume that you're always getting integers, because all we've seen so far is integers. So just do the really simple numerical addition. Don't do a JavaScript addition, which is really long. So we get new machine code from the optimizing compiler. So when we run the function again, we just use this fast code now. Do you see how this is better if you know that you're just adding integers and you can use that machine code instead of machine code that describes the whole specification? Yeah. Okay. What's the problem here, though? I mean, the compiler has no guarantee that you don't change your mind. This could be user input, it could be a corner case, it could be totally desired like that. There's no guarantee that just because we had integers 5 times, you don't change your mind. So what is the compiler going to do here? Well, we have this really fast code that works when you're adding integers. It would do completely the wrong thing if you feed in a string. So the compiler says, well, this is not what I optimized for. I go back to the baseline compiler, and we do the slow path again. So nothing bad happens. We just can't use the fast code, but we're not crashing. We're not giving you the wrong results. We just fall back to the slow path. So in our picture of the compiler pipeline, you have the baseline compiler, the interpreter ignition. You run this function a bunch of times. The first time you run it, we generate machine code for it, and then we use that machine code to figure out the answer is 43, 8, and 124. Eventually, we decide, well, we're calling add all the time. It makes sense to get better machine code for that. That's faster. So we pass it on to the optimizing compiler turbofan. And then turbofan is using that feedback or the information that we've collected before, that it's always integers, to give us really nice code here. And in case we change our mind, in case something like this comes in, well, we just fall back to the left side again. So the optimization in just-in-time compilers is a speculative optimization. You're speculating that the future is like the past. You optimize for that, and you always do a quick check. Hey, is everything the same as before? Yep, super, I can use the optimization. If you speculated wrongly, well, you just go back to the slow path and start over. Awesome. So we can speed up plus for integers versus strings. That's our main use case for JavaScript, right? I mean, everything is an object in JavaScript, and most of the time you work with really complicated objects, and it's fairly rare that you just have a naked number and you're adding them together. You usually have a bunch of objects, and you do operations on objects. So what about objects? Well, conveniently, this function has an object in it to show that. So we were doing object.x, so we're getting a property from this object. Object.x, just like the plus, it looks really simple. It's all over your code. It's a tiny little dot or the square brackets. You don't think much about it, but if you do think about it, there's a lot of things that could happen. I mean, first of all, you could have an error when you try to call object.x. It could be undefined. It could not be defined on object, but it might be on the prototype chain, so you have to recursively go up the prototype chain to look for it. Might be a proxy, or the X might have been defined ES6 style with an accessor, so you have all kinds of side effects. So it's not as simple as you might think from looking at the little dot. It's like a lot of stuff for the compiler. Again, the specification is quite long. Don't worry about what it says, just to give you an idea. There's tons of steps we have to follow in the implementation to produce correct JavaScript. So the trick that we're doing here is, so we're running our add example again. And the first time that we call it, we have to follow the specification when we want to get to the X. We have to check, is it on the object? If so, where is it? Should we throw arrows? Are there any side effects? And so on. Once we figured it out the first time, we put this information in a cache. And what we put in the cache is the shape of the object, and a shortcut to the value of x. So we're not putting in the object itself. We're not putting in the 42. We're just saying, hey, if you get an object that looks like a string literal, so, like an object literal, so in this case, no changes on the prototype chain, and it has x as the first property, then you can get to the value of x by doing this shortcut. So in V8's memory layout, that's just at a specific offset of that object. So we put in the cache the shape of the object and a short path to the value. And we associate that cache with the call side of this property lookup. So the next time that we call the function, when we want to get object at x, instead of going down the whole specification again, first we check the cache. And what we ask the cache is, hey, do you have something that has this shape? We're not asking for an object that has the x value 42. We're just asking for the shape of the object. And in this case, the shape is the same. I mean, these two inputs sort of look the same, just a little different number. And they also look internally the same for V8. So we can save this whole thing, and we just know, OK, this is how we get the value. OK, these caches, they're called inline caches. For historical reasons, they're not really inline anymore, but we call them inline caches. So you see a bunch of ICs sprinkled over our code base. And internally, we call the shape of an object a map or a hidden class. So, because in the past, JavaScript didn't have classes, and they sort of represent a hidden class. Like that's the class or the shape of the object that we internally associate with those objects. All right, so the graph again. We run the function. It runs in slow mode a few times. We collect information about the input. So we're collecting that it's a plus of integers, and we're collecting that the object is always this one literal that just has an x property and doesn't look different. And if the function is hot, we pass it on to the optimizing compiler. The optimizing compiler uses that feedback and generates much faster machine code. And if our optimizing compiler ever gets disappointed, if we are changing the kind of input, so here we're still having integers, but the object has a different shape now. It has two properties. So the shortcut to get the value would be different, most likely. Well, we just go back to the slow case and do exactly what the spec is asking us to do. So to give you the full picture of this, on the left side, that's 1/3 of the machine instructions for the unoptimized code. So it's like lines and lines and lines and lines, because it's really following this maze that we had in the specification. And these 4 lines on the right, they do this add function for this particular object shape. So very obviously, whether you do these lines or 4 lines, lots of times make a huge difference in performance. So you might, or I might have promised that in the abstract, some kind of performance advice. So with this understanding of some of the key concepts of how JavaScript engines work, in past talks, when we still had the old compiler pipeline, we had a few things that our optimizing compiler just couldn't touch. You might have seen advice like this, like don't use try-catch because it can't be optimized. Like none of this is true anymore because it's a whole new optimizing compiler. But the advice that I do have for you is write your code as much as possible to look like statically typed code. Like if you have one kind of inputs to a function, don't keep changing it. Don't use the same function to add numbers and to add strings and to add objects to it. Like, if you assume your language would be statically typed, then what you write is automatically good for the just-in-time compilers. So with that, if your code is statically typed in nature, then that is what's best for JavaScript engines. Thank you.
Hi. Hello. Woo. So write TypeScript is what you're saying.
That helps. It's not exactly the same times at the internal types, but at least you're not completely violating everything.
Okay. So I'm someone who loves theory over implementation. It's just implementation pays more. And so I love reading like specs, especially the ECMAScript spec. Do you find yourself working at the lower level of compiling, like reading the spec a lot and like, okay, so like, do you have any advice for developers who have been writing JavaScript and maybe have never seen the spec before on how to like get started without getting overwhelmed?
I think it's easy to get overwhelmed, but don't be discouraged. Just my advice would be always try to back up your intuition with an example. So read it and then write a small code snippet to see if that would actually correspond to what you assumed. Like try one of those weird corner cases and see if it follows the same branch as the spec.
Well, yeah, because I think that one thing that we like take for granted is how like not smart computers are, you know, like even at like the lower like assembly level, it's just adding and bit shifting. Yeah. So we like owe a lot to compilers for abstracting all of that. So like thank you for like doing that stuff so I don't have to think about it when I'm adding two integers or trying to add a number to a string and stuff like that. We did have a question on Twitter. Is there any hidden state when doing optimized hot compilation?
Is there any hidden state? I mean, there is a lot of feedback that we collect, like the type and the maps and the prototypes of the maps and so on. There's lots of stuff that's hidden and internal to the engine there, yes.
Cool. So one thing that I would like to see as people are saying like programming like on the web is getting harder. I think we're just getting more interested in how things actually work, and like it's hard, and that's why it's getting harder. I would love myself to see like IDEs and tooling get like more advanced, like understanding how the compilation's going. I think we depend a lot on like the terminal and stuff like that. Are you seeing like an evolution of tooling in JavaScript that like helps us think more about these things?
Well, in DevTools, you can get a really detailed look at stuff, and I didn't show that, but you can always start Chrome with flags, for example, to just print the bytecode that I showed you. Like just get regular Chrome, and if you start it on a terminal or Node.js and do -- print bytecode, you can see all these details. You can do print opcode to get the optimized machine code, and the ICs, these inline caches, so you can really, at a detailed level, figure out what you have there if you want that.
Imagine like, how long ago, God, I'm thinking like 7 years ago when I like just had Firebug to like inspect things, and look at how far we've come along with DevTools. Bless all DevTools teams.
Yeah.
Awesome. Well, thank you so much. Let's give a round of applause for Franziska.